short talk. It's going to be given by Ingrid Barcellos. And the title of the talk is Polaritons and Quantum Materials, Opportunities for Hybrid Light Matter Platforms at the Nanoscale.
Okay, so first of all, I would like to thank you, the organizer, for the opportunity to stay here this week and learn a lot of different things. As you can see, totally out of my field, but I believe that always a great opportunity to learn and make friends and maybe few collaborators in the future. Before my presentation, I would like to show the center that I work at. It's the Brazilian Center of Research in Energy Material. It's located in Campinas, São Paulo, near to São Carlos. It's a big laboratory composed by 4 national labs, one dedicated for bioscience, biorenewables, nanotechnology, and the big accelerator that I will show you here. And additionally, we have, in the last few years, the ILUM School. It's a school for science. So we are trying to to make more scientists for our side, the dark side of the matter. As you can see here in this image, is a big laboratory in the middle of the jungle. So few animals that our colleagues show in your presentation, we can easily see inside the campus. You can see several of them together with scientists. So we believe that many different specimens can live together. And if you don't have opportunity to visit us, I just to show here a quick video. It's 50 seconds, just in order to see you inside this big machine. So basically what we have here is the electron that can be accelerated near to the speed velocity. This is the real video made inside of our accelerator. As you can see here, we have 1,000 magnets that is responsible for, let's say, shaking this electron. And then, as you know, electron in high speed, when your trajectory is moved, they emit radiation. And this radiation is called synchrotron radiation. So we use this light. It's a broadband light for do different type of experiment inside this big one. I would like to tell you that there is nowadays 3 4th-generation machine like that running around the world. So this is one of them. And we have here several big lines fully dedicated for experiment and bioscience and condensed matter. And here, in this wall, there are many type of laboratory that is open for users and support you. One of that is the laboratory that I am a coordinate. It's microscope of laboratory, like microscope sample laboratory. It's a laboratory fully dedicated for sample preparation process. This is my team. There is a strange guy here. Sorry, it's my my PhD students. But as you can see, I have a, let's say, a family team. We can do more than sample preparation process, but we can do in situ material characterization and many techniques that will be complementary to experiment and bin lines. For that, we have 2 facilities. My mainly idea to show you what we can do, and obviously I not show everything, but I will show a few things that I believe is related to the presentation that I saw here, and then maybe we can do something together in the future for the experimental side. Okay. So we have a facility full dedicated for 2D materials. As I think Yara and someone presented here, there are plenty of them. We can do exfoliate. This material can be produced by simple exfoliated, and we can produce layers down one layer. They range. They stay in the range that vary between microwaves to UV. So there are many types of that, and obviously it includes 2D magnetics. So we can work with several of them. Obviously, I prefer the stable one for many reasons, but we can produce a lot of that. We have a clean room fully dedicated for that. As you know, we study fundamental physics quasi-particles, and the quality of the sample is related to the environment of the sample. So they need to say, the sample need to be clean. We can do simple exfoliation for materials. Also, we can place one on top with other. Inside the center, we have a National Laboratory for Nanotechnology. It means that we can do device, the simple one, field effector transistor, let more sophisticated one with many layers of 2D material as we can. And we can control the angle between these layers. And that, for the Moiré patterns here, in this example, I can show that we have a monolayer of one semiconductor on top of a monolayer with the other, with a zero angle between them, and here the same samples with 16 degree. I not say that it's easy to do that, because Ayara asked me many samples, but it's something that we can do, let's say, easily. Additionally, we have the microscope, the dual beam, that allows to produce many different building blocks. As you can see, we use here the xeno-ion beam for remove some part of samples, and we can nano-manipulate the samples and put everywhere. The same things we can do for lamellas with well-defined and polished interface. We use that for prepare sample for beamline. But yesterday, we saw in this presentation, yesterday, no, it's a few days ago, to Jair, that we can use this technique for produce microwave magnetic hybrid system. It's something new for me. I not use this machine for that purpose, but if you are interested to do that, we can do it together. Maybe when we come back to Brazil, write to me. But I'm not here to talk about facilities. I just to show the overview about what we can do in this laboratory. Basically, what we study is the quantum technology and low-dimensional material. There is many strategies to do that using two-dimensional material, to do the enhanced light-matter interaction that occur in this type of system. But today, I will specifically talk about the Polariton engineer in quantum materials that I think is related to what we are doing here. So we use Polariton for several applications in optics. The most simple one is using for sense. We can use the plasmons as a sensor for several molecules. We can use, again, phonon or other type of Polariton as a super lens, because the electromagnetic field is increased, and then we can see some structure behind the materials. It's a very common application for that. And nowadays, we can combine conventional semiconductors with 2D materials in order to do modulators, detectors, and so on. Polaritons, it's a quasi-particle described, I think, 1970 for the first time. It's a very old quasi-particle. However, the idea to study these polaritons and 2D materials, it's pretty new. And there are a lot of different things that can happen in the system. If you are not familiar with polaritons, we can describe it as a simple interaction. It's a coupling between the electromagnetic wave with some excitation of matter. If this excitation is the electrons oscillate, the electrons moving inside the metal, it's called plasmons polaritons. If the excitation coupling with the phonon, let's say vibration, we can call them phonons polaritons. There is different type of polaritons, exciton polaritons, magnons polaritons, and so on. However, when you see for the dispersion relation of these quasi-particles and 2D material, for instance, in plasmons, what we can see that the momentum of this quasi-particle, it's comparable to the confinement of light in order to nanometer. So what's happened in polaritons in 2D materials is we can propagate the light on the surface of the materials or inside the materials with the wavelength many times many times lower compared to the radiation in the free space. However, to probe these polaritons, there is a momentum mismatch between the incident light and the polaritons. For probe that, we need the nanometric probes. For that reason, it's very high to probe polaritons into the materials using the far-field conventional techniques. For that reason, we need to go to the nanoscale. And the best technique ever for see the polaritons wave and the real space is known technique, is the scattering type of near-field optical microscope, because we can properly see the waves like that, and we can have the precise control of the light at the nanoscale. And I will try to discuss a little bit about that. And a simple way to explain what's going on, this technique combines the FEM technique, is the technique that we can see details of the topography of materials at the nanoscale with the infrared microscope technique. It's a little bit more complicated, but I try to see just the general what it's working. But basically, we have the tip. The difference here that it's a metallic tip. When the radiation insists and this tip despolarize the tip, so this tip works as an antenna, it's a dipole. When the sample is placed near to this polarized tip, what we can see that the sample will be polarized as well. In more detail, we use the dipole model to modeling that, and we need to say that the electric field here, that we call it the near field, it's an evanescent electric field. So the scattering light from this small portion of the sample is proportional to the polarizability of the sample, and this polarizability is proportional to the electrical response of material. In summary, what we measure is the is-known signal, and the is-known signal is proportional to the effectivity polarizability that happened behind the tip. Okay, this is just a summary, what we know nowadays in that sense. So for explain what we can see in polaritons and different type of materials, we created here the, let's say, a fictitious dielectric function, because there is no material that it's a metal, semiconductor, and all those things together. And we can compare with the model that used for simulated these experiments, the dipole model. And what we can say that for metals, for plasmonic, we can use the Drude model, and we can match very well the permittivity with the is-known experiment. For phonon, for polar crystal, that we consider that is a strong oscillator, we know that there is a shift compared to the dielectric function and the experiment, but the community well know about that, and we can use this model for explain. For organic material, it's the perfect combination. We can see molecule using this technique, and we can, let's say, describe everything what's happened. For excitons, it's not true. There is many reasons for that. First of all, when we study exciton, the main of that is in the visible, and it's very hard to focus the wavelength of the visible radiation with the FEM tip. They are almost the same size, and there is other technique that can do it easily. And the question that I will try to discuss with you until the end of my presentation is how about Magnum? We can do that using is-known. So before to try to answer this question, I just want to show the full experiment and how you can do that for probing, let's say, polaritons. You can have a source, could be a laser source or a synchrotron source, doesn't matter. We can focus this light and We can focus the laser or the synchrotron source in a beam splitter. And this beam splitter used for this is a simple Michelson interferometer. We have the mirror that's moving and the fixed mirror. But in the place of the fixed mirror, we have the FEM. And then we combine those beams to detector. For the detector, as a result, we have the image at the nanoscale, the response of the material according to the excitation, in that case is the infrared, and also we can do spectroscopy with the same resolution of the tip. It means that we can do spectroscopy with 20 nanometers. It's a nanometer technique. But more than that, what's happened that this tip work is an antenna that launch polaritons with different types. Those polaritons propagate in the crystal inside or at the surface according to the type. They are reflected with the edge or defect or some other antenna in the material, and they are collected for the antenna again. And as a result, what we can see here is the standard wave formed between the tip, in that case in the edge, and this is the experimental result of that. We can see oscillations inside the material. When we're using laser for that, usually what the result is imaging of the polaritons. If you are interested to get more information about the dispersion of the polariton, we need to change the excitation, and then we need to align every experiment for each frequency. It's like a hell. So the good thing to work with a synchrotron machine that you have a broadband for that, and we can do everything in a single shot. So in that sense, what we can do is we can do many spectrum along of a line. In that case, we need to cross the crystal, and the response of that is that it's the map. When you have here the wave number as a function of the position. So here I stay on the substrate, and here is the material. And this high intensity that you can see here, we can select a profile, and we have the polariton profile. This is let's say, a damped wave, because there is loss in the real material, but we can extract the wavelength, the damping, the lifetime, and all those physical properties of this material, and we can compare directly with the theory without data treatment. So it's the most beautiful experiment that we can correlate theory and experiment, and just we don't need a sophisticated model for that. Okay, so now I just show what we are doing in that field. Since these materials, the polaritons into the material, will be observed for the first time. Let's show you that the first observation of polaritons into the materials is in 2011. It's not so, it's a very easy, it's a very new technique for mapping these things. And this is a revolution in this field, in plasmonic field, because in this world, the guy showed that we cannot not just probe polaritons, plasmons polaritons in a material, that we can show, we can simply change the dispersion relation of this material just to change the thermal level of a graphene. It means that if you have a device, we can change the bias, and we can automatically change the wavelength of the excitation. This is impossible to do using the plasmonic base in the metal, because you cannot control the wavelength. If you want to do that, we need to produce new nanoparticles with different shapes or with different metal. So this is, let's say, a fancy model to do that. After that, few years later, we show that there are some materials that support hyperbolic phonon polaritons. It means that different from the plasmons, the polaritons here can be propagated inside the crystal, as a cavity mold, as a photonic crystal. And the good idea to study it, that if you are interested to do some metasurface or so on, basically what we do is put different type of different type of materials in order to do many combinations. And using 2D materials, we can do that easily with a few nanometers. It's very easy to do that. And we also mapping the exciton, polaritons, and TMDs. The mainly advantage in that case that you don't need to do sophisticated device. We can just change the thickness of the crystal, and this is enough for turning the polariton properties of 2D materials. And obviously, if you know that we can probe plasmons polaritons and phonon polaritons, the next step is combine both. And here start the study with hybrid polaritons. But the good idea to combine materials in that sense that support different type of polaritons, there are two. First of all, we have the heterostructure, that we have some frequency where the phononic character is preeminent, but in the same way, do you have any frequency that the plasmonic character is preeminent, and we have hybrid modes, like here, that is not appear in those systems separately. And I will give you more details about that regarding what we are planning to do with magnons in that sense. A little bit late, we are trying to see new materials that have these properties, because until now, we don't have more than 5. And obviously, we start to put some antennas in order to control the light propagation. This is the new revolution, and this, let's say, in that sense, because it's possible to do experiments in cryogenic condition. Just to exemplify how important it is, this is the imaging of the first experiment here, 2011. And here is the same graphene, the same sample in low temperature in a device. And we can see that no more than 4 oscillation here. And here we can see the propagation for many microns. So it means that we can reduce the loss of these quasi-particles, and we can do some of the optoelectronic devices. This is the idea. Okay, but all those experiments that I show here is made in the mid-IR and in the visible. But we know that if you are interested in magnons or magnetic material, we need to extend the frequency range for the far IR and terahertz. Sincerely, I don't believe that we can extend more than that. It's a limitation. But more than that, if you are interested to study materials and that energy range, there is no laser cover continuously this range. And for that, we need to go for big machines or big accelerators, synchrotrons or free electron laser. But we don't need just a source. We need this source coupled in the FM tip. And nowadays, there is just 3 places around the world that you can do that. And it's make this experiment a little bit difficult. And the second challenge is the tip. When we work with the long wavelength, we need to long tip. And this FM tip is not available commercially. So what we do is using the FIB and the other technique in order to fabricate our own samples. But it's working well. In the last few years, we show many different works that this is the first experimental observation of phonons, polaritons in terahertz regime. So we produce some nanocavities. This is the simulation of our experiment, that we can see some light inside the material. And here is the experimental data and the line profile that show that we really do some nanocavity of light inside the crystal. It means that we are excited the material with the light around the 50 micrometers, and we can confine the radiation inside the material with less than 100 nanometer. The confinement factor is more than 200 times. And then we can perform some devices to show how can I control that. And more recently, we extend a little bit more the experiment, moving to the low wave number, to the real terahertz. So there are many things in that sense happened. Okay, but this year, what we are studying, when I say what we are studying, I'm talking about what the community in this area is studying. I don't know how it's working in magnonics, but in your field, and 2D materials, as you can see, it's a very new community. Everyone knows the other. So we can share the results, the development of machines and technique. And the bad thing that you know who is the guy that review your paper. So, but okay. What we are doing, this sample now, the technique now, it's in the state of art. Let's say we can do the twisted layers. This is the image of my last paper. As you can see, the 2 graphene layers, the idea is 2 graphene layers, rotated, one related to the other. When you do that, we can form this kind of structure with a different stacking. And using the Snow technique, believe me, there are some, let's say, dot here. It's here. It's clear to see. Clear to see this configuration. It means that we can use the plasma polaritons to reveal the structure of twisted graphene and almost atomic resolution. But more than that, the last one, this is the new, I believe. It's possible to do the same experiment that I show you here in cryogenic condition and apply magnetic field. So this is the state of art that the people are doing in this field. We can do a device using magnetic materials, and we can apply perpendicular magnetic field. And the idea here, it's mapping polaritons or magnetic polaritons using the Snow technique. And it is working. Actually, there is just one equipment that's running around the world. It's a Rome-made one in the Stony Brook University. They building a cryo snow and applied magnetic field. It's working well, but it's a very difficult system to operate for many reasons. It's a homemade one. I believe that in 1 or 2 years, we have something like that available for Bio 1, I hope. But what I need to pay attention here is that there is a little bit more than 10 years and in this area. And the only magnon polariton is not mapping using this technique yet. And according to development of the tools, the community are in this way. But there are many questions that we don't know how to answer yet. But I need to say that we started in that sense, not for mapping polaritons, but for studying magnetic materials using the Snow technique. The first thing that we did, and I believe that is the most important part, the most important step, is the extension of the frequency for low frequency regime. So this technique working well in the terahertz. As I told you, I don't believe that we can extend more than that, unfortunately. But it's possible to measuring magnon polariton and IAG materials or the other ferromagnetics. We can do everything, combine cryogenic Snow and magnetic field. I think this is working well. There are many 2D magnetic materials that we are studying now. It's new for everyone, as Yara showed you here. So there are many things to do, but sincerely, we don't know how we can correlate the spin-light coupling and this type of experiment, and how we can include in the theory the magnetic component. This is something that the community, I hope that the theoretics is working that. But we have a few solutions that we are trying to do in that sense. It's very similar to that Yara show in his presentation, because we know exactly how the phonon polaritons work. We know exactly how the plasmon polaritons behave. We can calculate everything for that two quasi-particles, and the idea is we put materials, magnetic materials on top and try to coupling these quasi-particles, form the hybrid modes, and try to understand what is the difference that appear when we put a magnetic material on top. Okay, will it be possible to real space image of magnon polaritons with this now? Until now, this is just a dream. But let's say it's not just my dream, but it's a dream for the community that work with this technique. Obviously, we need a lot of input of the people from the other side that work with magnon polaritons, but maybe in the near future we can do it together. Just a final remark, 1 minute. As I told you here, we work in an open facility. So the sample preparation process and these known techniques, we have the beam line to work in the media IR and the terahertz as well. It's open the next semester. Users is always welcome. So if you get more information about how to use it, let me know. And thank you for your attention and for funding agencies.
Thank you very much. So the talk is open for questions.
And the answer is, I don't know. Okay. No one knows.
Thanks a lot for the talk. I mean, I'm not from this field. For me, well, I mean, polaritons, I know that are cavity polaritons, and where a magnon couples to the cavity field. And there, this cavity field is magnetic.
Yes.
Now, in your case, do you know, is it magnetic field or electric field or both?
In my case, without external magnetic field, it's electric field, but we can apply magnetic field in the system.
Yeah, but you apply static magnetic field. Now I'm talking about terahertz field.
This is something that we need to develop. This is what we cannot do for the moment. Yeah.
Any other questions? I had one question. So do you have any particular materials in mind for these 2D materials to look for magnon polariton? Any materials that are kind of promising, most promising?
I'm not sure here because it's, let's say, a little bit out of the field, but I'm working with natural materials. It's minerals, it's 2D minerals. And from my state, from Minas Gerais. And it's a very interesting material because they support different type of polariton. And there is a paper published last week that show they are magnetic also. So I believe that's a very good platform because it's easy to coupling different types of polaritons in one material, let's say, but it's something that I will study the next maybe year. Long time.
Any other questions? All right, if not, let's thank Ingrid again. And let's thank all the speakers for today.